Hello everyone! Today we'll begin a 5-part series on hash functions.
Hash functions are unkeyed cryptographic primitives that have many applications.
Chapter 3 on hash functions is comprised of 5 video lectures. In V3a, we'll define hash functions and describe 3 applications to motivate the main security requirements of preimage resistance, second-preimage resistance, and collision resistance. In V3b, we'll explore relationships between these 3 properties. Then, in V3c, we'll study generic attacks on hash functions, including Van Oorschot-Wiener parallel collision search. We'll introduce iterated hash functions in V3d and summarize the checkered history of hash function design. Lastly, we'll present the SHA-256 hash function in V3e.
Hash functions play a fundamental role in cryptography, and they've been used in a variety of cryptographic primitives and protocols. As we'll see, hash functions have been proven very difficult to design, in part because of very stringent security and performance requirements. Over the years, many hash functions have been broken. The main candidates available today are the SHA-2 family, of which SHA-256 is the most commonly used hash function, and the SHA-3 family. Informally speaking, a hash function is a fixed public function that takes as input a message of arbitrary length and outputs a hash value of a fixed length. In some sense, the output serves as a fingerprint of the much longer input. You can check these 3 websites for calculators for the hash functions MD5, SHA-1, and SHA-256. The most widely used hash function today is SHA-256. This function produces hash values of bit length 256. For example, the SHA-256 value of the ASCII message "Hello there" is this 256 bit string written as a hexadecimal string of length 64. The hash of the slightly modified message "Hello there," where now the T is capitalized, is this hexadecimal string of length 64. This string seems to bear no resemblance to the previous hash value. So the idea behind hash functions is that for every message, the hash function outputs a hash value that appears random and has no apparent resemblance to the original message. Of course, the description of the hash function is public, and so anyone can compute the hash value of any message. However, without the description of the hash function, you can say nothing at all about the hash value of the message other than its length, which in the case of SHA-256 is 256 bits. Formally, a hash function is a mapping H that maps binary messages of arbitrary lengths, at most L, to outputs of a fixed length N. So this is the domain of the hash function, and this is its codomain. Usually L is very large. For example, L might be 2 to the 64, whereas N is small. For example, N equals 256. Also, the hash of X should be efficiently computable for all messages X in the domain of the hash function. H is called an n-bit hash function, and H of X is called the hash value or the message digest of the message X. Note that the description of a hash function is public and fixed, so a hash function has no secret keys. To ease the notation, I will usually write 01 star instead of this more descriptive notation to describe the set of all binary strings of length at most L. Here is a toy hash function. The domain of H is a set of 01 strings of length at most 4. And the codomain is the set of binary strings of length 2. Columns labeled X in the table are the elements of the domain, and columns labeled H of X are the hash values of these elements. For example, the hash of 0011 is 00. I'll call 00 and 1000 a collision for H, because the two messages 00 and 1000 have the same hash value, namely 11. I'll say that 1001 is a preimage of 01, since the hash of 1001 is 01. I'll say that 10 is a second preimage of 1011, since the hash of 1011 is 01, and the hash of 10 is also 01. Hash functions are used for all kinds of applications that they were not designed for, and for this reason, it's sometimes difficult to assess security of these applications. One reason for this widespread use of hash functions is the speed of hash functions. I'll next present 3 desirable security properties for hash functions. The first desirable security property of a hash function is preimage resistance, or PR. PR is the following property. Given a hash value y, selected uniformly at random from the codomain of the hash function, it should be computationally infeasible to find with a non-negligible success probability any message x such that the hash of x equals y. I'll call x a preimage of y. I'm using the words any and a here because the codomain of a hash function is usually much smaller than the domain of the hash function. And so, one can expect that for each y in the codomain, there are many x's in the domain whose hash equals that y. So H is preimage resistant if finding any message whose hash equals y is computationally infeasible.
Allow me to interject that in the definition, the success probability is assessed over the selection of the challenge y and the coin tosses made by the preimage finding algorithm. The requirement that the preimage finding algorithm find a preimage with non-negligible success probability is needed to rule out trivial preimage finding algorithms that are very fast but only succeed with negligible probability. For example, the preimage finding algorithm that, when given a challenge y, simply selects a random message x and outputs x, will only be successful with probability roughly 1/2 to the n, which is negligibly small.
Preimage resistance is required if hash functions are used for password protection on multi-user computer systems. In this application, the server stores user IDs and hashes of passwords of users in a password file. When a user wishes to access the server, she enters her user ID and her password. The server computes the hash of the entered password and compares it with the hash of the password in the password file. If these values are equal, then the server grants access to the user. An attacker who gets a copy of the password file doesn't learn any passwords. She only learns the hashes of these passwords. In order to impersonate the user to the server, the adversary will need to find a message, not necessarily equal to the password itself, such that the hash of the message equals the hash of the user's password. The attacker can then enter the user ID and the chosen message, thus gaining access to the server. So for security, this application of hash functions requires preimage resistance. The second desirable security property of hash functions is second preimage resistance, or 2PR. 2PR is the following property. Given a randomly selected message x, it should be computationally infeasible to find, with non-negligible success probability, a second message x primed different from x, with the same hash as x. 2PR is needed if hash functions are used as modification detection codes. To ensure that a message m has not been modified by unauthorized means, one computes the hash of m and somehow protects h of m from unauthorized modification. Protecting h of m might be easier than protecting m itself, because h of m is in general much smaller than m.
Modification detection codes can be used for malware protection. Imagine that a user Alice wishes to download a piece of software X from a website that might be untrusted. Suppose also that Alice somehow has an authentic copy of the hash of X. Alice might have obtained h of X from the print copy of a trade magazine. So, Alice will download X from the untrusted website, compute its hash, and compare the hash value with the hash value from the trade magazine. If the two hash values are equal, then Alice installs the software on her computer. An adversary, who wants Alice to install a piece of malware, needs to format the malware X' so that the hash of X' equals the hash of X. In other words, the adversary needs to find a second preimage for the message X.
So for this application to be secure, we need H to be second preimage resistant. The third security requirement for hash functions is collision resistance, or CR. CR is a property that it is computationally infeasible to find with non-negligible success probability two distinct messages X and X' that have the same hash value. I'll call such a pair of messages a collision for H. Note that H usually has many collisions, since their domain is usually much larger in general than its codomain. So by the pigeonhole principle, there are many pairs of messages with the same hash value. Hence, the issue isn't whether collisions exist, but whether one can find a collision efficiently. Collision resistance is required when hash functions are used to compute message digests in digital signature schemes, which we'll see in Chapter 7. For reasons of efficiency, instead of signing a long message, the signature scheme actually operates on its much shorter message digest. This application requires preimage resistance, second preimage resistance, and collision resistance, as I'll explain in Chapter 7. For now, let me explain why collision resistance is needed. Suppose that the legitimate signer Alice can find two distinct messages, X1 and X2, with the same hash value. Recall that the signature scheme operates on the message digests rather than the messages themselves. And so, we see that Alice's signature on X1 is also a valid signature on X2. Hence, Alice can sign X1 and later claim to have signed X2. In this way, she might be able to repudiate her signature on X1. To prevent this from happening, we need H to be collision resistant. Hash functions have many applications, and we'll see some of them later in this course.
In Lecture V3b, we'll investigate the relationships between the three security properties of hash functions: preimage resistance, second preimage resistance, and collision resistance. I hope to see you in V3b.